Happy Friday, TGIF, right? Gonna finish up looking at tangent planes, right? I believe we left off with implicit differentiation. Right, we're given an implicitly defined function, and we wanted to find partial z, partial x, and partial z, partial y. Right, so we wrote big F, right? So we always want to write our implicit equation as some function of x, y, z, or if it's a three-variate function, x, y, z, w equal to 0, right? And then we say, well, then that left-hand side is our function big F. Our goal now is to find the partials, right? Since we want both partial z, partial x, and partial z, partial y, we're going to want all three partials. Right? If we just wanted partial z, partial x, we'd only need fx and fz. What's fx?
Y cosine xy plus z cosine zx.
Okay. What is fy?
X cosine xy plus z cosine yz.
And finally, fz. Bella, don't forget to sign in. And then while you're doing that, I'm going to quickly get up and steal your food.
I cosine yz plus x cosine of zx.
Now we have those, the implicit derivatives is very simple. Partial of z with respect to x is just the partial of f with respect to x, negative partial of f with respect to x over partial f with respect to z. I did write that order as zx. I'm going to keep it that way, even though it doesn't matter. And then, of course, you want to always ask yourself, can that be simplified? This one cannot. Partial of z with respect to y would be negative partial f with respect to y over partial f with respect to z. They're your partials. A lot easier than doing it the Calc 1 way. It is left as an exercise for you to verify that if you were just to do the implicit differentiation as you learned in Calc 1 and algebraically solve for partial z, partial x, and then partial z, partial y respectively, that's exactly what you would get with a lot more algebra. What we're going to do is show that the equation of the plane tangent to the surface f of xyz equals 0 at the point x naught, y naught, z naught is given by that equation. Right, so in the video that's on My Open Math, it's derived for surfaces of the form z equals f of xy. This is now doing a method if the surface is implicitly defined, right? Because remember, a lot of curves are implicit curves, right? Like a circle. Well, same would be true for a lot of surfaces. So a sphere would be implicit. We're going to look at an arbitrary curve on our surface that passes through the point. Right, so just say that curve is R. Then at P, must have the partial of f with respect to x times x dots. Remember, that's derivative of x with respect to t, plus the partial of f with respect to y times y dot, plus the partial of f with respect to z times z dot has to be 0. So that has vector equation of the vector fx, fy, fz dotted with the vector x dot y dot z dot equals 0. Which means the two vectors are perpendicular. If we take a look at x dot, y dot, z dot, that's r dot. Well, that gives us a direction vector for the tangent line of r at P. This line must lie within our tangent plane. Well, we just said that that vector is perpendicular to the tangent vector. But that tangent vector has to lie in the tangent plane. So that vector is our normal vector to the plane. Remember the equation of a plane? It's A times x minus x naught plus B times y minus y naught plus C times z minus z naught equal to 0, where A, B, C are the components of your normal vector. Which is precisely what we wanted. So now we're going to be able to find tangent planes of surfaces of the form z equals f of xy and implicitly define surfaces of the form f of xyz equals 0. But P is our point. Right, because you got to remember with tangent lines and tangent planes, it's at a specific point. I want to show that these two surfaces, F and G, are tangent at the point 2, 1, 1. Well, if the two surfaces are tangent at a point, wouldn't it mean that they have the exact same tangent plane at that point? So it's going to suffice to show that at 2, 1, 1, they have the same tangent plane. Well, it's the same point. So all we're really going to have to do is show that the normal vectors for the two planes are parallel. If they're parallel and we're at the same point, then clearly it's the same plane. But remember, what we say the normal vector to the tangent plane is? This guy right here. We need f sub x, f sub y, and f sub z. What is fx? We just need to evaluate that at the point P. What is fy? That needs to be evaluated at P. And what is FZ? That also needs to be evaluated at P. Be what? 2 times 2? 8 times 1? Negative 8 times 1. So there is the normal vector for the tangent plane to F at the point. Do the same thing for G. So what is G sub X? No, that wouldn't make sense, would it? There we go. So what is GX? Right, as before, we have to evaluate each component at P. What is G sub Y? Right, that's that P. And then finally GZ.
plus 2.
Four minus 6. -2. 2 minus 6, -4. 2 plus 2 is +4. There's the normal vector to the tangent plane of G at the point. You should easily see that they are parallel. That's all we had to show. So the two surfaces are tangent at that point. They were going to show that the surfaces F and G are normal at the point 121. Which suffice to show that at that point, their tangent planes are normal. Right, that means that the angle between the two tangent planes is pi over 2. How did we find the angle between planes? Feels like forever ago.
So we set cosine theta equal the normal dotted with each other over the magnitudes multiplied by each other.
And so we just found the angle between the normals, right? That's all we have to do here then. Show that the normal vectors are perpendicular. So we need only show that their normal vectors are orthogonal. And again, normal vector to the tangent plane is given by partial with respect to x, partial with respect to y, partial with respect to z, and then evaluated at the point. What is fx? Fy And then finally, FZ. You said y minus 4. The 2 minus 4. 1 plus 1. And 2 minus 4. -2, 2, -2 is the normal vector for F. What is GX? GY. And GZ. Normal vector for G is -5, 1, 6. Perfect. Take the dot product. The dot product is 0. Means the two vectors are orthogonal, which is precisely what we wanted. Any questions? Next week, we'll be looking at directional derivatives, which will finish up multivariate functions. Well, the initial study of multivariate functions. I mean, second test you can expect next week. Also next week, we start multiple integration. And that's where things ramp up. We'll see how quickly I can get through it. We start by looking at double integration, and that's broken into 2 topics. We first just consider the easiest type of double integral, which is that over a rectangular region. Then we look at double integration over more general regions. I might be able to get through both. We'll see. If not, then the general regions will have to be after spring break. Because the week after that is then spring break. So fun times about to begin. We're already halfway through the semester. I will tell you, you may want to brush up on your trig. That won't be until definitely after spring break is when we look at polar integration. So over spring break, you may want to brush up on all of your trig because there's going to be a lot of it. Also brush up on your polar coordinate system. It's going to be very important. After double integration, we look at triple integration. Right, again, that's broken into two types. We look at triple integration over the simplest region, which is a rectangular box, and then triple integration over more general surfaces. Concludes by looking at triple integration in cylindrical and spherical coordinates. So multiple integration, I think we're looking at what, 2 weeks, maybe 2.5? Two and a half weeks of multiple integration. Then we look at vector analysis, which basically takes everything that we've done in calculus. That's in one chapter. Whole crux of Calc 3, as I mentioned, is 3 theorems: Green's theorem, Stokes' theorem, and divergence theorem, which is the end of vector analysis. So we're getting into fun times. Finally. Did I misnumber something? Didn't we take quiz 11 already? I'm gonna double check that. I think I misnumbered. I think this is supposed to be 12 and let's label this.